So, welcome everyone. I think we should continue and looking a bit at Docker. Just as a word of warning, I'll probably leave very timely today because I have another class at 1 since Maish and Simon are overseas, not overseas, somewhere else in Europe, whatever. So, so last session we started talking about Docker. I'm not convinced we got very far. So you guys still don't really have a full insight of what it probably is, but I asked you to create an instance of, or a virtual machine in particular, on OpenStack. So we have something to work off, or you have something to work off. And we continue with that today. In fact, just looking at how we can actually, get more comfortable with Docker and the whole idea about writing containers on top of a virtual machine, so we can actually share the underlying operating system, because that's something you will need to do for the third assignment anyway. So just before we get there, so yesterday I uploaded the an updated slide set that contained the command for actually installing a latest Docker version under Ubuntu, right? If you have a VM, run those commands without the bullet points, obviously. They just signify that they are new commands. Well, not really, but you should be able to run those ones. And they basically, what they do is update the packages, install some additional packages that you need, then download the, I mentioned that before, the key for Docker, for a Docker repository, and adding this to the permissible, repositories that Ubuntu can install from, then fundamentally adding the repository, then running an update, and ultimately installing Docker, the community edition, CE. There's also an enterprise edition called EE. If you browse for ways of installing Docker on your machine, you often find that they'll just ask you to run sudo apt-get install docker.io. If you do that, you get a kind of an outdated version, as I mentioned before, on your machine. So please avoid this, otherwise you will eventually get stuck with the things we're doing here, because there are some features that are not have not been integrated in the previous version. All right, so what we basically have is now a Docker command line. So and it's fundamentally the idea that we have, simply the Docker command. So I'll just go into the virtual machine I created yesterday. That was the one I created. And before we get deeper into it, there was already one comment regarding errors that you possibly have if you perform certain operations on the system. And well, we'll probably do that once we encounter this error again. It's probably easiest. So I first run sudo docker images, right? So Docker relies on root access, so it needs to have access to the underlying infrastructure, so you won't get around running sudo. So as soon as you do that, you get all the images, and the image we see right now is called Hello World. Surprise, surprise. Fairly small, but that's the default image. You would just want to try run that anyway by just running sudo docker run hello world, and it will automatically download and run it. So what you see here is the comment says sudo unable to resolve host class instance, and this is not related to Docker. It's related to the
Increase
the font size. Yes, I'll try that. See how that goes. Yes. 10 point is not enough, isn't it? So, let's see. That's a bit better. Does that work, roughly? For the ones that are following. Cool. So, so again, I just ran sudo docker images. We see all the images. So here's the relevant output. So those are the header lines here: repository tags, image ID, when it was created, and the size. And so a repository is basically a name. Each repository can have a tag as well. That, in this case, the default tag would be latest. That is the latest version of a of an image. Then the ID, unique identifier, and when it was created, and ultimately its size. Here into 2 lines basically. So if I widen that a bit, probably have a bit more structured output. Cool. But coming back to this issue here, unable to resolve host class instance, and it boils down to a lack of configuration when the images are instantiated in OpenStack. So class instance is the name of the host that I gave it during when I created the image, and the way of dealing with this, or the reason for that, is that it actually tries to resolve its own host name upon every sudo operation, but it's not able to do that because it's not contained, not resolved by a DNS server or the local hosts file, so which is this one here. And so if we substitute or if we append the entries for the local machine, so then we should be no longer getting those issues. So basically what I did was just now, so I ran sudo nano etc hosts, and then we get basically opens this host file in nano, which is like a shortcut for the domain name resolution system, right? So it uses the local hosts file. It's the same in Windows and in Linux, but just to get that done, and then you enter this entry here. You point the local host IP address 120, the local loopback IP address 127.0.0.1, which you guys know is always pointed to localhost. Yeah? No? Perhaps? Yeah? And you associate it with the name of the instance that we gave it. So hopefully now the issue should be gone if we run Docker images again. So now you see it's running without that problem because it can resolve itself. On the other hand, if you can't be bothered to deal with this, no harm either, nothing will happen. It's just this that you get this annoying error message, but it will not produce any different output or affect you in any way. Yeah, just to let you know in case you don't want to deal with this. But you know, anyway, we got rid of it. So now we basically have the clean output of sudo docker images. Right. So let's get into it. So we want to create images, and fundamentally the idea of doing that relies on the Docker command. So if we want to figure out what Docker actually does, it's probably worthwhile just running sudo docker help. And that gives you an overview of all the available functionality that is basically available here. So we're obviously not looking at all the different commands that are available, but just to give you an intuition, here's the overview. The more relevant ones for us are down here. So those ones here, the commands: attach, build, commit, cp, create, and so on. And they all basically are system level operation that either involve instantiating a Docker instance. So Docker run is an example for this one. So it creates a new container and runs the command in it, or simply instantiates an image. You can also delete running containers, rename them, show the images. We ran sudo docker images right now. Copy files between container and the local file system. So sometimes you want to have files from the local file system that you want to copy in the container, and obviously building them. So those are some of the main commands that we'll be dealing with. We're not exploring all of them, and you don't need to learn by heart right now, but we just explore how they actually work. But before getting into that, there's two words that you find that are confusingly used here. One of them is called image, the other one is container. Yeah, let me see.
Could you remind me what was image in this context?
Yep, exactly. So I want to get to that. Does anyone have an intuition what image means in that context?
Is it the image that the Docker container is based upon?
Yep, that's right. So what's the relationship between image and container?
A container is the changes of the image. Or, yeah.
Yeah. So if we put it in, probably the easiest way to conceptually is to put it in kind of OO lingo. How's the relationship between images and containers?
I didn't hear what you said, sorry.
In object-oriented lingo or terminology, what would be the relationship be between image and a container? You say the changes upon? Yep. Yep.
Container is the instance of an image.
Exactly, right? So the image would correspond to a class, let's say, right? A fixed baseline image that has a fixed setup in terms of operating system, perhaps additional tools. And then you can have multiple instances of this one, right? So, and those would be containers. So the image just contains a baseline software, if you like, or not at all. There's actually an image that's called Scratch. So if you want to write something from scratch, you literally get an empty image you can work off. But the idea is that you have basically a blueprint for an instance, and that is basically an image, yeah, containing software. In this case, we have one exact image that we downloaded before, which was the Hello World one. But you could, for example, also download a baseline image containing only Ubuntu. Yeah.
So Docker is for changing the operating system?
No, Docker sits on top of it. As we discussed yesterday, we had a look at the schematic overview. So we have the underlying hardware, operating system, then Docker services, or the daemon if you like, and then containers within. However, Docker transparently allows the containers, so if you have multiple containers running, to access operating system functionality without changing the operating system. Yeah, it's only accessing the operating system. Anything that needs to be persistent or related to the particular instance needs to be contained in the container itself or in an attached volume. We'll talk about this concept later. So that's the key idea, that you can have multiple isolated applications that just directly operate on the operating system, but don't affect each other. So basically isolating different applications. That's the key idea. So I brought up this, I'll probably bring up the schema again. That probably makes it hopefully somewhat clearer here. If you look at the third one on the right, so that's literally it. So we don't have really an operating system within the containers. It sits below that, right? So like the Linux installation or Windows installation and so on. But
didn't you say the images were like operating systems?
They can contain operating system software, but they are not the operating systems themselves. They're basically just relaying any request that's coming in to the actual underlying operating system, to the underlying Linux. Yeah, so they're using transparently the underlying operating system, but they are not the underlying operating system.
Okay. Could you give an example of an image?
Yep. So we will deal with various images. Hello world is one of them. We're just simply executing a command. In fact, we can probably easily inspect the structure of such an image. In fact, that's what today is about. So, one of the way of inspecting images, by the way, it's like the ecosystem, a bit like the App Store for Docker, is the Docker Hub. We'll see if we find the Hello World image there. That's the official Hello World image. Note before I go into that. Notice here this. So if you do a search, you generally have mechanisms of assessing the popularity or quality of an image. That is generally either by stars or by the number of pulls, right? You notice that how often actually an image has been pulled. It's usually a good indication because everyone is free to publish their own images, so you kind of need to do a critical assessment. But I can actually go into it and have a look what's happening here. So this is the basically official repository for the Hello World image here, and it's basically the simplest possible way of basically Hello World equivalent for Docker. And right, so let's have a look into. Let's see if we get insights into the Docker file, how it's configured. Right. So what this does, and that's literally everything that this image is built on context. So it starts from scratch, meaning it does not provide any image-specific additional software, but it directly relies on available operating system functionality. Right. So it's not the operating system itself. It relies on operating system functionality. It copies the command hello. To give context here, there's an executable which is called hello. It's copying it into the root of the image, and then it's executing it. So once you start that image, there's the only thing it does is starting that image and executing this executable down there. Yeah. So you see there's no explicit installation of an operating system there. Does it make sense?
Yeah, but I'm still not quite sure what it's used for, because here it's just used for.
That's right, but you didn't even let me get to that stage yet. Okay. So we just had the discussion what it fundamentally is. Now we get to the usage as the next point. Yes, please.
Maybe it's worth mentioning that Docker is just change root on steroids. That it hides the system resources.
Yes. Exactly, but I'm not sure if we should go down that route and discuss the underlying fundamentals. Okay. Because yesterday I touched on C groups briefly, control groups. Yeah. And they have similar elements, basically about selective sharing, but you're right. Yeah. So we have insulated environments, isolated environments or views on the operating system that can't affect each other, basically. That's the key idea, right? So again, the operating system, some Docker in the green here, and then the individual containers. So, and containers can be built based upon different images, right? So we have a selection of images, and we can instantiate one or more of them in a given runtime. The good part is, since they're independent from the underlying operating system, it's also easy to share them, right? They're rather small, and ideally, that's the key thing, you want to kind of formalize the any image explicitly. So here, for example, even though the image is basically to us accessible as a binary, hang on, let me go back to where I came from. That was here, as a binary hello world here. Docker is about specifying the underlying code, right? So how to actually build and rebuild this image. So by downloading this Docker file associated with its context, so basically that folder here, that folder, so including Docker file and hello, you would be able to rebuild this very image that we have right now. But we didn't do that, we downloaded it directly. So the build image can be downloaded directly, so you don't compile it from scratch. That's fairly similar to what you do, but Docker integrates those two processes directly. So there's not much complexity involved in terms of building. You generally just call Docker build on a Docker file, and it will execute it. But we get to that in a second, before we get even lost in those high level and the specifics at this stage. So how does it fundamentally happen? Talked about this. Don't want to go into this one. Yes. So the fundamentally workflow for working with containers, especially if you just want to create containers, meaning work off an existing image, is that you find your image of choice, using Docker search in the command line, which you can do. We have one. So Docker search, for example, well, let's do hello world, and you'll find that it actually links against the same, sorry, I forgot sudo. So you get that kind of stuff. It means you forgot sudo. Usually a good indicator is permission denied. So, so we need to run that with sudo. So if you run search hello world, you'll find, well, you see pretty much the same output you saw before, because it is fundamentally the same output from Docker Hub. So we have an image called hello world, and that you can basically pull them, which we did already, but the command for doing that would be sudo docker pull hello world of the image you want to actually run. Could also be one of the other images. And if you're not specific about the tag, so again, because images can have tags, you could have different versions. Docker is really about tagging and versioning as well, because you want to be very specific about the image that you want to run, right? So a download. And if you don't do it, it will look for the tag latest, which is the default tag, and download the image. But in this case, the image is already downloaded and up to date, so it actually doesn't really do that. So we should have the image already in our repository, in our local file system, right? So download image hello world here. So, so as I mentioned before, once you have that image, you can actually just run it ideally, and it should go as far as to say sudo run hello world in this particular case. No, not world, right? So and it will instantiate the image and produce some output. In our case, the output is quite straightforward. It literally says hello from Docker and gives you a bit of output. So it's very simple executable, but not much magic. So. But if we look now to differentiate between containers and images, we can actually look at the available containers in our system. So we can do that using Docker PS, but it won't really show us anything right now because none of the containers is actually running. But if we run sudo docker psa-a all, it will also show you containers that are not actually running anymore. And you notice that it corresponds neatly to the containers we have been running before, right? So we had been running hello world once, and we had been running it a second time, and it basically does something which is producing the output and then exiting immediately. So it's not a persistently running application, right? So it doesn't have a daemon attached or web service or anything like this. So we have all the images here, and sorry, all the containers here, and then we basically just have container ID, the image they correspond to, the internal command that's executed, when they were created, and the status, the current status of execution, which is exited. In our case, it's probably worthwhile just to delete them outright. So we can refer to them by their generated alias here. You can also assign aliases during execution or tags during execution. So this would just delete the first one, and this one would be the second one, so we don't need to, we don't keep them handy. So if we run PSA again, now we see we don't have any containers left, they're all gone again. But again, it doesn't affect our images, right? So the images are there as they were before. That's the key idea. So to perhaps show a more involved way, we could bring up a... So the question is now, how can we use that productively? So it was the question, okay, how can we do some magic in there? And obviously the Scratch image is very limited in its functionality, but you can also build up richer software environments, such as full Ubuntu installation, right? So if say, for example, you want to pull an Ubuntu image, we could, for example, first identify, okay, which images are available. So let's say you want to get the latest Ubuntu or one Ubuntu. You'll see there's a considerable selection available here. So the highest starring here is Ubuntu itself, and again it corresponds to whatever you find here in the Docker hub. So from a searching point of view, it's oftentimes more convenient, unless you constrain to command line, to actually deal with the Docker hub itself. And you'll find that there is a large number of different tags. If you just call pull the latest, you get a specific, well, the latest Docker version, which would be probably 1710 right now. If you look at tags, latest, yeah. But you can also you can identify them by any of those specific tags. So, for example, if you want to have an Ubuntu 14.04, you indicate it as well. So let's just pull an image and we do that saying sudo docker pull Ubuntu, and I want to be using the latest. So let's see how it goes. So what you see now here is actually that it's well, downloading literally a full Ubuntu image, and it does so in different slices. So the idea to parallelize the download and speed it up, all images are produced in individual slices or layers there that are then downloaded, so it makes it usually quite a bit faster. So the idea is, once you did this, you have the image available in your local repository, so we suddenly have an Ubuntu available, which we can now productively use if we want to. So in one way of building, there are basically two ways then to actually use those images. Either you directly run a container and configure it. This is something we probably should just explore. And the other way would be to write a Docker file and build a container from scratch. Those would be the two ways to interact with this. So if we now have this Ubuntu container here, we can just run it interactively. So how do we do that? We say sudo docker run, and then indicate that we want to interact with the Docker container, and we need to identify the image we want to build it from. Hang on. Cool. All right. So what do we have now? If you noticed here, so we have created a container and immediately interacted with this. You notice that we suddenly have this weird host name here. So our host name is no longer class instance, which was the machine I'm working on, this, the virtual machine, but in fact we're now inside the Docker container itself, right? So you can run ls, and you see a different file system sitting below here. So if you look, for example, in home, there's nothing like a home, in fact, right? It happens so that containers are executed as root. So the only home directory that's relevant is actually root directory here. But other than that, it looks like a fully fledged Linux. In fact, Ubuntu in this particular case. So most of the applications that you find in Ubuntu are available here. So it also means that we can do stuff like installing packages. For example, if I want to install a web server right now, let's use Apache 2 for this example. I could just run apt-get install Apache 2. Note, I don't need to use sudo here because we are root already, right? So we're directly executing with super user permissions, so no need to run any additional sudo. Unable to locate package. What did I get wrong? Hang on, did I get anything wrong? What is going on? It seems it doesn't have, oh, that has connectivity, so probably just got the package name wrong. So the apt-get install Apache 2 commands. What am I missing? Ah, no sudo. That's better. So, okay, I forgot to update the package list. So it was an empty image, but it didn't know about the available packages for Ubuntu because I needed to run the update first, which downloads like a catalog of all available repositories for this particular Ubuntu version. So after doing that, I can just run install Apache 2, and which hopefully installs the Apache 2 web service. That's the key idea. It takes a while, but hopefully then we have a running web service set. So in the meantime, I'm spinning up a second instance. It does it on my main screen. A second terminal instance, so we can actually inspect running images. So again, I'm on SkyHigh again, logging in here, and then jumping back onto the very same instance. If I get my password right, yeah, it looks about good. And that would be this one. So if we now run sudo docker ps, so we're now on the very same machine, but not inside the image. Again, recall this is running within the image, this is running on the host. We'll see that there's actually an image running right now, right? So that's Ubuntu latest, has been started 2 minutes ago, and we're executing the bash environment. And if you find that the container ID actually corresponds to the one we're actually operating on here right now. So it's oftentimes a good idea to perhaps start 2 instances of the terminal so you can actually see what the other terminal is actually doing, what the other process is doing. Hang on. Just increase the font size here as well.
This stuff only works with Linux?
Traditionally, yes. So Microsoft is currently rebuilding its architecture to natively support it. The older versions basically used VirtualBox as an abstraction layer on Windows, basically to run Linux in there and then to run Docker in there. But there will be native support on Windows, yes.
I'm just thinking of these images. You can only pull from like, you can only pull, well, you have the underlying operating system.
Yeah.
So all the images, they would have to be restricted to whatever the underlying operating system.
That's right.
Provide.
Yes.
So that's like, all the images are like subclasses of the operating system, and the operating system is like a superclass, which has like, you know what?
Yeah, I know what you mean. So I know what you mean. You basically need to adapt to the abstraction layer that's provided by our operating system to use its functionality, right? So the commands that it basically provides, right, or functionality.
What I'm thinking is that if there is some Linux which has some quirky functionality, you will not be able to use that image on Ubuntu, for instance, if Ubuntu is the underlying operating system.
Yeah, well, it does actually translate that coherently. That's the key idea. So that's the challenge with Docker, that you have a standardized infrastructure that allows pretty much anything to run on any operating system-ish. There are limitations in practice, but that's why it's under continuous refinement. No, it's by no means final in its way. And but the vision is to have a generic container format that is totally independent, hopefully totally independent of the underlying operating system eventually. But it's a far-fetched. Well, it's a continuous effort to actually do that, right? So yeah, but that's the vision here. So I think we're nearly getting there because Apache 2 is setting up, and I just wanted to show basically how that could work. Yes, that's right. So something that's probably inside full. So we now looked at the container. Let's look at the image we downloaded just to give you an intuition of what we're dealing with. Note that the Ubuntu image that we have here is still about 122 megabytes in size, right? So there's a considerable addition of software right now, but by far less compared to what a complete Ubuntu install would consume, right, on your operating system. But still, 122 megabytes is something we can't neglect. So once this one here is done, so Aperture 2 is just a web server, pretty much the default web server, increasingly replaced by Nginx, I guess, but still quite popular. Come on, just wrap it up. And then we'll see what the image looks like in the end. Right, cool. So there we are. So we basically now have a installation of Apache. It's not really running yet. What we do now, we want to maintain and keep the state of that image, right? So we can leave the image right now, and then can run now back on the host. Can sudo docker commit. So it was the commit command. And if we now know the ID of that container, hang on, I need to get that ID from here, 52A2 BFB 3D 89F. Cool. So this is the container identifier, and we want to give it a name, right? For example, well, I just make something up here. Ubuntu Apache. Let's see if we get away with that, or if I. Cool. So what we have done now, basically, so if I run sudo docker images again, we have now created a new image from a container. And we did this by, again, instantiating a container, doing stuff to it, you know, changing, and then committing it. And at this stage, it's actually, you know, written as an image, right? So, and we call this image Ubuntu Apache, and you note now the size has increased considerably, right? So that's all the stuff we just downloaded and has been melted or first, you know, amalgamated into the original image. So we can now instantiate this one. So you probably want to run it, and we can see how far we get with this one. So running this image is somewhat specific to the way you start Apache on Linux. So there will be a bit of additional syntax that I will explain once I type it out. So we first say sudo docker run. If you use the name parameter, you can instead give the name, the instance, a particular name. Recall, previously the container didn't really have a meaningful name, right? So it was just called having some unique identifier, but you can make it more meaningful, so it's probably worthwhile doing that. I call it my Apache right now, so it doesn't matter really what it's called. And well, should we do it in advanced? Oh, we'll see how far we get here. And this provides original one additional part of the syntax here. So we say do sudo docker run, we give it a name, and then we have -p. And -p is for redirecting ports. So since we can run an arbitrary number, or basically only one constraint by hardware, number of images on a given machine, we need to clarify how we deal with networking, right? So which network port on an image, for example, an image could always listen on port 80, if it's a web server, for example. To which port of the operating system or on the host that we're running it on should we bind it. So you specify the host port, and you specify the image port that it binds to, right? So if the image is listening on port 80, you want the host to listen on port 8080, sorry, then that's your way of specifying, so -p. So then we need to have the image, which happens to be Ubuntu, we're basing it on that image, Ubuntu Apache. And then we want to run a command on that image. And that is basically running the Apache command tool. So we have some meaningful output. And that's basically just taken from the documentation of Apache. It's not specific to, well, it's specific to Apache right now, how to run it. And what it does is basically running it as a foreground instance. I will run -d here, which means run the image and detach from it. So otherwise you will be, basically your console will be attached to the image. So any output that's produced by the image would be shown on the console. So now we're running it, please. Yeah, Amisi, please. What does it say?
Foreground, you're running the command. Why would you run it in the foreground? Or have I misunderstood the difference between background and foreground?
That's for Apache. You run the Apache executable inside the container in the foreground of the container. But if you don't connect the output of the container to your console, you don't see anything from it. That's the idea. So now I need to figure out why this actually didn't work, which is not good. But we get there. So sudo docker run. I think our container is. Let's connect to the container. Build a new instance and actually connect to it to see what's going on. So sudo run docker t. And I want to bind ports again. Hopefully the ports are not bound anymore. No, double. Don't need that bit. Okay, so the command I was supposed to run sits in user cd bin. So now I'm debugging basically of what went wrong here, why my Apache stuff doesn't start, if it was a typo on my part, or if it's simply not existing. Okay. Find name Apache 2CTL, that's what the one I want to look at, and it sits in user sbin for whatever reason. So if you run this thing, user sbin Apache 2CTL, what is happening? Yeah, it says it runs, so that's cool. So why doesn't it run when I started from the outside? It's probably also a typo on my part. So okay, let's exit. So cool. So I'm now back in my main instance, right? You notice that I exited or left the container, and the container is no longer running. So I need to restart yet another instance. So let's try my luck again here. That was what I was running before. Ah, right. I got the folder name wrong. sbin, right? So it was in Apache sbin. So this is the Linux command for looking for files. So it's find. Then you specify the starting location of your search, which is /. So I want to look throughout the entire file system. I'm looking for a file with a name. I'm not looking for its size or date or whatever else. And then the actual name you're looking for, because I know the executable is called Apache 2CTL. So coming back again, extending on Amisi's concern. So we're starting a new container based on Ubuntu Apache, running this command inside the container, but detaching, using -d, detaching the container from the output console of the host operating system. Make sense?
That sentence is very long.
Okay, I structure it. So 2 layers. I'll probably draw it. Cool. So this is the host we're dealing with, right? So that's the host machine we're working on right now. So then we're creating a container. This is the container. And this one is based on the image. Let's use a bit more color. Ubuntu Apache. Recall that this image was originally based on the image Ubuntu, right? So that's where complexity starts, right? So we did this first. We built an image, and then a container committed to it, and it became an image. Yeah, Ubuntu Apache. Then we instantiated that container. Right, and now I want to run a command. This command here, /user sbin Apache 2CTL with some parameters. Ignore the fact that it says foreground, just some parameters to a command, right? I want to execute it in here, right? So Apache 2CTL, whatever, control, is executed in a container, but at the same time I use the -d parameter for Docker. It says, well, whatever that container does, even if it does it in the foreground, don't bind it to my console. If I omit -d,
what does bind to console mean?
Sorry?
What does bind to console mean?
I think we probably just do it. It will show any output on your current console. So let's do that. It's not detached. The problem is actually if you do use SSH, it generally hangs. Then afterwards you can't control it anymore, and the instance hangs, which is not a big deal. But that's right. Hang on. It's already in use by container. Right. So what you see here, the error says, well, conflict. Sorry, the container you name you're suggesting to use, my Apache, is already in use by an existing container. So what the system says, hang on, you still have an outdated container sitting there. You can't just reuse the name if you are not getting rid of that container first. And that's the one here. So the one is called my Apache. So what I will do is now delete this particular container, sudo docker rm my Apache, so I can reuse that name, for example. Yeah, so I instantiate a container from that image with that name and execute things in foreground. Good luck to us. And that probably, yep, that's cool. So that's Apache starting. It's not fully configured. That's why it gives us this output, but that's fundamentally okay. So what binding to console means now is that we can't do anything anymore. You notice that we're now basically just hanging with the output of the instance. However,
you're starting it.
Yep.
I was going to say in the background, but it says in the foreground, so it
yes.
can't be in the background.
So it's in the foreground of the container, and it's bound to our Docker environment. Yeah. If I had done -d, it would still run in the foreground in the container, but wouldn't be binding and blocking our command line input. Yeah. But you find that it's still running. So here now from the other instance, I just ran sudo docker ps, and you see the image is actually running and hopefully binding to port 8080. We can test that by running localhost wget. You guys know wget, right? Ish, yes, perhaps. It's just, you know, retrieving stuff, and we see, yeah, indeed, we get some index file presented on port 8080. If we look into it, yeah, that's basically a dummy file from Apache just telling you, congratulations, you set up a proper Apache instance. It says something like that in the beginning. Let's see. Yeah, here. So Apache 2 Ubuntu default page, it works. So basically, we have now a web server running on port 8080 on that system. Yeah. So unfortunately, we don't have any GUI access directly. I think I have a Windows instance we could probably use, or app use for that. See if it's running properly. Because Windows running Windows in OpenStack is actually a bit heavy, but I have an instance here. I'm actually surprised that it's working. So what we could do now, if we wanted to access it, we need to get the ID of the host, which happens to be 133. So recall that was the ID that was the floating IP that's defined in OpenStack, right? So now we need to actually identify the host the Docker instance is running on, and then on port 8080, and we should get that output. So there you go, we get the Ubuntu default presentation. Okay, cool. So, but that shouldn't distract us here. So now we basically have that image that is yeah, bound to my console, which is semi-uncool. Yeah, that was the other one. Good. So what I can try to, so Control-C generally quits the container instance, but in this case it won't work. It won't just relay the signals to a Docker container. So my only way of dealing with this is actually of stopping it from the other console that I still have. So sudo docker ps shows all the running containers, and if you say sudo docker stop and identify a container, my Apache in this case should work, then it should stop the instance. Could take a bit. And release the associated resources. Yeah, perhaps not, perhaps yes, we'll see. Pain and agony. Well, eventually. Well, while this time's out, I'll open yet another instance. So, there you go, it came back. So I actually did it. So we run sudo docker ps now. There's no running image, but you find there's a set of outdated images, including the latest one we just ran 3 minutes ago, and it has exited. So what's happening here now? Yeah, we're back to our command line, right? So, okay, had we done the same thing with -d, just for the sake of showing it, we wouldn't have that problem. So we, hang on, it's already, we need to delete the name again, or change the name to something else. Let's say my Apache 2. and it's actually starting the same container, but this time it actually doesn't bind the command line to it. So basically it's running independently. That's kind of what you want in the server environment most of the time. Once it's actually starting up, you don't want to be bound. You just want to operate. So it will take some time to come up, but eventually it will. Right, so that was part one. There you go. Yeah, so it's actually running, and then eventually will come back. It just created the instance, gives us the ID back. Cool. So, all right.
What are some of the uses of having multiple images? What are some of the uses of having multiple?
Yeah. So first of all, images are totally independent of each other, right? So they can either build on each other. So you can have an image that builds on top of another image. We just showed that for the Ubuntu Apache case, right? So you can incrementally build. It would be good, for example, you have a baseline software and you have customizations for different, clients, customers, and so on, or a production one, experimental one. You want to run different, software on top of it as a baseline configuration, but they can also be totally independent. So, for example, you could run your database server or container and your web application server, which is fundamentally one application but split into two containers that are then isolated and therefore, possibly more reliable. Independent from each other. So the idea of images doesn't tie you down as to what you run in it. There can be dependencies between images, but they don't have to be either. Yeah. So that's the key idea. So what I wanted to do is to show you Apache. That's what I called it, right? Yeah, there you go. That took ages. Well, so when you look carefully at images, so your way of actually exploring images, and that's not the default way of looking at it, but so if you say sudo docker inspect and you name the image name of interest, you can find information and meta information. For example, repository tags, the parent. So if it's built on another image, that's actually the parent image. So relationship is maintained. And various further information. So, for example, the host name is contained as well. So a lot of meta information, environment variables within that particular image, right? But at the bottom here is something, so I'm not going through all those little things here, but at the bottom you find something that's quite important. You actually find a notion of layers. And that's precisely pretty much the question, well, similar to your Git repository where you have different commits building on top of each other. Here you have image layers building on top of each other. Right, so this image, for example, consists of 6 layers of different stages in which the image has been built. Yeah, so that kind of has the kind of a versioning feel to it or principle to it, as we know it, for example, from conventional versioning systems. So before I let you into the break, one question I had to ask. By the way, here our image is finally up, so we can just say sudo docker ps again, and it shows that now our Apache is actually running somewhere on the Docker as a Docker instance, but it's no longer binding our console. The question now is, what we did was basically interactively building a Docker container, right? So or Docker image, and then container, modifying it and creating an image of it. What's the downside of that approach, possibly? Yep.
Seems like a lot of work if you're going to do this for every single one.
Okay.
So I have a question if this is easily scalable.
Right. Okay. So number one, obviously the building the image is a one-timer, right? So from now on, the only thing I would be doing is create new instances of that one here, right? So I rerun that command and call it my Apache 3, 4, 5, 6, 7, 8. Right, and change the port name and so on. So once the container is built, it's relatively easy, one command away of instantiating. So I think you can still automate that bit. But
you could build some other software to run the command for you.
Yep.
But I'm thinking about having this run by itself to meet demand.
Yep. Yeah, that would be the next thing. So Docker itself does not deal with scalability as such. It's just about the infrastructure of containers. When we talk about scalability, we will talk about it. That's the next step. Right now, it's just the underlying technology that allows us to build containers. Right? We get to that in a later session. The question I have though is, what is the problem with the approach we just took? or that I just took by interactively creating a container. What's the problem with it? Does anyone see any challenge? So what happens if you think you're building on top of this? Remember, we just built this Ubuntu Apache container here. And now, down the road, I actually find out, oh, cool, I actually need to have a particular, web page on it, right? So, cool. So I create yet another image from it, right? So then I create instances from it, that is fun. So then we find out we need to do yet another modification of the web page, for example, or a variant of it, even worse. So we have two building of it. Different websites for different, customers and whatsoever. What's the problem with this? Yeah, please.
If you change the nodes further up in the tree, you change all the branches.
Yeah. So in fact, you're creating new branches. In fact, because there's no way of pushing that through recursively. So you would need to create new images. Yeah. But what's another issue? Let's say you're shipping this image to someone else and they're built on top of it. What do they know about this image here? Do they know how it's constructed, or do they need to know? Right, you have the image sitting in Docker, right? You run Docker images, and everybody's happy to instantiate it, add yet additional software, and commit that, right? So having a new image based on it, and it can be instantiated into various containers. But is there any problems in terms of that? If you're running software for a long time, for example. Any concerns? Yeah? So the problem is that usually if we do those kind of things, we generally think about long-term maintainability, right? But if you seriously do that approach, and you have multiple people building off the same image, and they don't really know what went into the image, you have what is called the golden image effect. So suddenly, this thing becomes, because that's the one that worked, it becomes super holy, right? And you keep track of that image, because nobody has any clue anymore what happened here, what someone did in there, right? Because I was interactively typing in there, I was basically just mucking around, and something runnable came out of it at the end. But it doesn't mean that those people can ever really retrace what I did in here, yeah? So it's not transparent. Instead, we want to have a transparent process that allows us to, that's why we do compilation, right? So we basically build from source to binary, not only to have platform dependence, but also to ensure that, platform-specific binary, but also to ensure that our source actually corresponds to the binary that we're actually executing, right? So we're not just passing a binary around, but we don't know anymore what's sitting in there. Yeah, it's the same as copying a binary around. Instead of doing this interactive approach, we should just use Docker files to basically specify the build process and automatically run this. Yeah? That's the key idea. And that was something we do in a few minutes. So after I give you like 10 minutes, and then we do the same thing transparently. So you have one file that does everything for you, so we don't lose track of that. Because if I were to ask you to redo what I did just now at home, that one is not going to happen, right? So, or most likely not particularly successful, especially in the long run. But the idea is that the whole process is self-documenting in Docker. And that's kind of one of the key merits of it, because complexity is very, very high, especially if you have a large number of containers. You still want to keep track of actually what's running in there. Yeah? So the whole idea of the build process is built into the whole framework, similar to Go, where the whole build toolchain is also built into the programming language. Yeah? Cool. So I give you, what's the time right now? 12:10. 12 until 12:20, so 10 minutes of break, relief, stretching, hot chocolate, whatever you need, and then we continue and see if we can get a image build from scratch briefly. Yep.
I sent them a mail yesterday and then.
Yeah. To Mariusz? To whom? To me?
No, to the group.